So our next speaker is, will be Ralf, and he's going to speak on OpenLDAP high availability. Ralf is a longtime contributor to the OpenLDAP project. Been on the engineering team for many of years. At SUSE, you work mostly in Linux directory services and supporting a lot of really interesting Linux deployments around the world.
Right.
So here's Ralf.
Thanks. Hello, everybody. Yeah, Kurt introduced me already, so I don't need to do that anymore. I will show you today setup, high availability setup for OpenLDAP, completely based on open source software. And I will first give an introduction to some general concepts of high availability. I will not go very deeply into the details. And then I will show you how the setup is done, show you some details about the configuration, and if there's time left, I will try to do a demo if that works here. So what is high availability? It's basically the ability of a system to continue to provide services even if one or more components fail. So the goal is to reduce outages to a minimum and to recover fastly if there is an outage. But the main goal is to have no outages at all. So as a very simple everyday example, we can take this picture. You see there's a car on it. It has, if you can see it, it has a flat tire. And we can use it as a very good example to introduce some basic concepts of high availability. One important thing is if you have a failure, you need to be very fast to detect it. So fault detection is a very important part of high availability. If you are fast to detect a failure, you have a good chance to be fast on recovering from that failure. So for this example, in the car case, it's very simple to detect the failure because, well, if the tire is flat, you immediately notice that. So for software, it can be slightly more complicated to detect failures, actually. Then, another important concept of high availability is redundancy. The redundant part in this image you see there is a spare tire lying around that you can, well, almost everybody can easily replace it with the things that the car is equipped with. Usually, car is equipped with a spare wheel. You have all the required tools to replace the wheel, and usually you can, well, if you're not, if you don't have two left hands or something, you can recover from it. So recovery is the other important, another important term when it comes to high availability. And there's another one, reliability. Even in this example, even with a flat tire, and because the car is equipped with a spare tire, you can be sufficiently reliable because it is possible to easily recover from that failure. And then there's another important thing, which is testing. If you once did change the tire for training it, for practicing it, it is very easy and you will be faster to recover from the failure. So with that, we switch to computing. And this is a formula how availability can be measured. MTBF stands for mean time between failures, and MTTR is mean time to recover. So often you see this high 99.99 something numbers expressing how available a system is. Unfortunately, this number doesn't say much about when failures happen or what kind of failures happen, and it's more or less a marketing term. But what you can learn from the above formula is to increase availability, you either have to increase the mean time between failures, and this is mostly done by, well, buying reliable hardware or software so that it doesn't fail that often. Or you have to decrease the time to recover, and that is done by doing good monitoring, detecting failures very fast, and have procedures in place to recover from failures. And another thing is to be able to recover from failures, you have to, well, have redundancy to replace broken parts fast. If a switch breaks in your network, you can't wait for the vendor to deliver a spare one and wait to have it replaced. It might take days or something, so you have to have a spare one which you can put in place. So in computer systems, we often use failover clusters for this. So basically, this is how a failover cluster works. Yeah, you have two servers, basically installed the same software on both servers, and if one server is currently active, this one was, in this example, this one is, where is it? Or this one is server A, and when this one fails, well, the other one immediately detects that it failed and takes over the work of that server, including, in this case, for example, the virtual IP address that's printed in red there. And the connection to the shared storage is also transferred to the other server. So there's some terminology used for high availability clusters that is important to know, because every documentation about clusters usually uses these terms. The first one is nodes. That's just the computers participating in the cluster. Then their cluster has resources. This is basically all kinds of software applications or IP addresses or everything that runs on the cluster. Then there's a split brain scenario, which is well, in a high availability cluster, the nodes rely heavily on communication between. It's very important that there's a working communication link between all the nodes. If communication between the nodes fails, you have the split brain scenario, and the cluster has to recover it from that somehow. And that's done by quorum, which is a kind of voting mechanism where all remaining nodes in the cluster try to communicate with each other, and well, they are counted, and the part of the cluster that has the most votes will continue to be will form the new cluster. Every other nodes in that cluster, every remaining nodes that can't communicate anymore now need to be cut off from the cluster. This is called fencing. Fencing is a very important part of clustering, especially if you use shared storage or something. You have to disconnect every node that cannot communicate with the other nodes from resources like shared storage, so that they can't write any malicious data to it or something. So fencing is implemented can be implemented in two different ways. One is resource level fencing. That's usually implemented by denying the specific node's access to some resources, or for example, by firewall rules, or by denying access on the fiber channel switch or something. And another one is node level fencing. Node level fencing is basically just you connect to a remote switch and remote power switch and turn off all the failing nodes, hardly like powering them off, and then they can't do any harm anymore. And this is very well visualized in this picture. This is how node level fencing works. So they basically, if any of the servers fails, they shoot each other. One shoots the other one. It's also referred to as stoneth, which stands for shoot the other node in the head. It's the cluster people have some sense of humor, I think. And this is basically the introduction about high availability. And now I'm going to introduce the setup that I'm using here. This is based on Pacemaker. Pacemaker is an open source project implementing for implementing high availability clusters. It's kind of the successor of Heartbeat. I guess most of you have heard of Heartbeat already. Pacemaker is kind of based in the community of the Heartbeat developers, and is supported by most large Linux distributors, SUSE, Red Hat. I think some Debian people are also active in that community. And it provides a few different components. One component that is not part of Pacemaker is the first one I list there is membership and communication. This is when you set up a Pacemaker cluster, you can use two different implementations for that. And the one I'm using here is CoroSync, which is basically just a communication layer for clusters. It offers reliable messaging for the different nodes. Then the biggest part, or the other parts of Pacemaker, is a resource management daemon that provides. That's a central process coordinating the cluster. Then there's a cluster information base. This is a configuration database of the cluster. It's an in-memory database based on XML, and that it's distributed between all the nodes. Usually you don't have to touch this XML. There are nice management tools that you don't need to write any XML configuration, because that can get pretty complex. Then there's a policy engine which has intelligence based on some rules that you can define which resource to start on which node, and which server to kill, and these kind of things. And then on every node there's a local resource manager. This is basically just an abstraction interface to be able to start and stop resources on a node. The local resource manager uses the resource agents, which are another abstraction layer for being able to map a specific resource, like for example OpenLDAP, into the local resource manager, so that it provides a standard interface so that for starting and stopping and monitoring resources. It's very much, the resource agents are very similar to System 5 init scripts. I guess everybody of you has dealt with System 5 init scripts, and look, the resource agents are very similar to that. Yeah, then there's StonysD, which is the fencing implementation for Pacemaker, and then there are some management tools. There is command line tools and a simple GUI tool where you can view the current status of your cluster and can define resources and so on. Pacemaker knows a few different types of resources. The first one is called primitive. It's just a single service that you start on one node, and basically you start always with defining a primitive. So if you want to start OpenLDAP on a single node, you define a resource of the type primitive. Then you have the choice to group primitives with other primitives. This would be a group resource. So you can define that specific resources need always to run on the same node because they have some kind of dependency. And then there's a resource type of clone which defines that primitive resource can run on all nodes at the same time. So, for example, for OpenLDAP, you can run an OpenLDAP instant on every available node and have replication between them. And there's a special type of clone resource type. It's a master-slave resource. I haven't listed it here. It can be used to have the resource running in different modes on different nodes. For example, for OpenLDAP, you can define that there needs to be one master node and several slave nodes running on different servers. The master-slave resource has the ability then to promote or demote specific nodes from master to slave and back in case of failover. And then you can define constraints between different resources. There's a co-location constraint where you can say that two resources need to be running on the same node, or there's an order constraint where you can define that resources need to start in a specific order. So that, for example, if you have a DNS server that uses an LDAP database as its backend store, you can say, okay, the LDAP server needs to be there before the DNS server is started. So in the demo setup, I will use an OpenLDAP resource agent, which is not yet available upstream in the Pacemaker project, unfortunately, but there's some development going on, and there is discussion on the upstream mailing list for including it. It was not developed by me, it was developed by a third-party developer for his own use, but it seems to be working pretty well already. It supports slapdconf and backconfig configuration. Unfortunately, for backconfig, it still reads directory files itself instead of using slapcat or something. But it only reads, it doesn't touch the configuration, it's read-only, so it's not that bad. And it implements some basic monitoring by issuing a configurable LDAP search command to the server in different intervals. And yeah, it was initially developed for Debian system, but works very well on most other Linux-based distributions as well. Okay, here's a quick overview how the setup looks like. So we have basically a two-node cluster. Pacemaker is running on every node, and you have Pacemaker running here. This one is like the connection between the Pacemaker. Like there needs to be a heartbeat signal so that they know, they are aware of each other, that they know if the other node is still up. Then we have two OpenLDAP instances, running mirror mode replication. And yeah, one thing I need to mention here, it's the setup I'm introducing here is very simple. I don't use any, I wanted to use mirror mode replication and only have one active writer node. So no real multi-master replication, but only one of the servers is accessed at one point in a time. So there's a virtual IP address that is either mapped to this node or this node. So it's just a simple failover. If this one fails, the virtual IP address will be assigned to this one. So it's a very simple setup. But I think for the beginning, it's good to start with a simple setup, especially in high availability environment. If things get complex, things will fail. So staying with a simple approach is probably the best. Then we have two Stonith instances on each node, which control, like, yeah, the power switch. In my example, I use virtual machines on a single computer, so it's not really a practical example for real-world usage to have a two-node cluster on a single computer, but for demo purposes, it's okay. The Stonith, in my case, is implemented through libvirt access, where the virtual machines can connect to the host, which runs the libvirt daemon, where they can just power off the other node through a simple command. I will show the configuration soon. Yeah, now let's start with a demo. I need to prepare some things. Oops. Oops. Next try. Okay, this is Word Manager running on my local computer. I have the two nodes here, which I just started. Should be up pretty soon. But this is not so important. We access it through SSH. Okay. The nodes have, I make it a bit larger. The LDAP server or the virtual IP for the nodes is this one. Is I'm not sure, can you see it or is it still too small? Okay, this is a virtual IP. This is the one that the LDAP clients will use to access the service. And this is one that will fail over between the different nodes. So now let's take a look at the configuration. Server should be up meanwhile. Ooh. The main configuration tool is called CRM. It offers a simple shell-like configuration command line. I will move the window a little bit. And the configuration, basically, this is the cluster configuration. You see, yeah, this is, for example, the configuration of the virtual IP. It's a primitive of the result. This is a, oh, shit. this is the name of the resource agent that manages virtual IPs. This is the IP address. This is the interface to which it is mapped, to which is assigned. And this is defining that it's monitored every 5 seconds with a timeout of 20 seconds. Then we define a primitive of the slapd resource, where we say where the slapd binary is, where the configuration is located, as which group and user it should run, and which listeners it should use. And this is used for the monitoring task. This is the name of an entry that should be read regularly, and if that fails, it considers the service to be failed. The migration threshold is an attribute defining that after trying to start or restart the slapd resource for 3 times, if that fails for 3 times, the cluster resource manager will no longer try to start slapd on this specific node. I will show you in a bit how that works or what that does. It will just basically not start the slapd on that node anymore, consider it failed, and move the IP address, if it's currently assigned to this node, to a different node. And then I define that the monitoring task should run every 10 seconds. This is the next one is a definition of the Stonis device, which is we use, as I said, again. As I said, it's based on libvirt. We define which node name is the mapping of the nodes to of the host names of the nodes to the name of the virtual machines in libvirt, and we provide an URL how the libvirt daemon is to be accessed. And this one is mirrored every 15 seconds, which is, I think, the default for this resource. Then we define that slapd is started as a cloned resource, so it started on every node at the same time. And we define the Stonis resource is cloned. That's basically what you have to do always. And then here are 2 constraints. The one is co-location. You always want to have the virtual IP running on one of the nodes, which also has slapd on it. This is basically what is defined here. And this is an order constraint that you say the IP address is to be moved to a resource before starting slapd on that. It's moved to a node before slapd is started on that node. These are some general options for Pacemaker, where you find that you use OpenIS, which is another name for Corosync, for messaging. Then this is the expected quorum votes. It's as we have a 2-node cluster, quorum doesn't work exactly. If one node fails, you only can get 1 vote, which is never the majority of all available nodes. So we simply need to disable quorum in this cluster. So quorum only works with clusters larger than 3 nodes, and it's basically always a good idea to have an uneven number of nodes in the cluster to have quorum, at least. Otherwise, if you have a 4-node cluster, the quorum expected quorum votes would be 3, but for 5-node but if it splits in the wrong way, you can't get a quorum anymore. If you lose two nodes, you won't get a quorum anymore. So this was the cluster configuration, or the Pacemaker configuration. I leave that for now, and then I show the OpenLDAP configuration, which is pretty straightforward mirror mode. Let's do LDAP search. I think it's easier to view. A pretty normal mirror mode node configuration. You have You have to define server IDs for every node. It is important to use the host name of the machines here, the one that the machine, that, for example, the host name -f command resolves to. Otherwise, replication can act funny. Let's say this. Because the server IDs are an important part of the mirror mode replication. Then, this is a schema that is not that interesting. And then we have the databases. There's a configuration database. You have to load the sync provider overlay on every database. That is this one. And you have to have the sync REPL configuration, which is this one. Every database needs to have a sync REPL configuration for every participating node. The sync REPL client will ignore the one which is mapped to itself. So I'm currently on node 2, I think. This node will ignore this sync REPL replication. It will not start to replicate from itself. So it will only replicate from node 1. Then there is another important thing to note. I use start TLS for protecting the replication connection. You have to make sure to add the correct IP addresses and host names to the certificate, so that certificate verification works correctly. So that means you have to add the virtual IP under which the clients access the server, and you have to add the different nodes, at least if you want to use a single server certificate. You can also use multiple certificates, different certificates for replication and for normal operation. But in this configuration, I use just a single certificate, which is configured here globally. Yeah, basically the same configuration for the normal database. Here's sync REPL definitions, and one thing I forgot to mention is mirror mode equals has to be set to true for this to work. Otherwise, the mirror mode replication will not accept, or the config, I think the back config will not accept multiple sync REPL definitions. And yeah, mirror mode equals true. Then you have, of course, to allow the identity which you use for replication to have read access to all data, which is defined in this ACL, which is very simple, might not work in a real production environment, but basically something like this. And of course, you have to set the limits high enough so that this user can read every entry. So this is a basic overview of the LDAP configuration. Now I start the UI tool for the cluster configuration, or for the cluster management. It doesn't need to run on one of the nodes. You can have it run on a client. It will connect remotely to the cluster and needs authentication for accessing the cluster. This now populating will take some time. So here you see, it's not a very nice overview, but here you see all the nodes in the cluster, the resources we defined, and you see, for example, this is a virtual IP. You see that it's running currently on node 1, and all the other resources are fine so far. Everything is green here. So let's see what happens. Okay, I have here an LDAP search, which is running every 2 seconds on the virtual IP address, just for demonstration purposes. I leave that running here. Start another terminal. and connect to the currently active node, which was node 1. Yeah. And now, oh, it's a bit tight on screen space here, so I'll move it here. And now I will just, as OpenLDAP never crashes, I need to be brutal and will just kill the daemon. And you see, yeah, you should briefly see it here. Was this one? It already restarted. You see it has a fail count of 2 now. I tried it before presentation, so it already had a failure count of 1. Now it has a failure count of 2 and was just restarted on 450, which is now. Now I kill it again. And now it has a fail count of 3 and it's not running anymore. That's what the migration threshold refer to what I explained previously. So now SLAPD is not running on node 1 anymore, and the IP address was automatically migrated to node 2, and you see the LDAP search is still returning successful results. So now to have it running here again, I need to clean up the resource, and then it should be automatically restarted. The IP address still is running on node 2 because there's no reason for migrating it back. Okay, for migrating it back to the other server, because basically they are the same setup, both are masters, and there's no reason for migrating back. So now I will show a different thing that is, for example, I will just, you can migrate it manually, for example. I can say, I want to migrate this one to node 1 and do it now. And now, yeah, the IP address is back at node 1. I can also show the configuration here. No, it's not here. This is funny. I have no idea why that didn't work. It's obviously still, no. Probably, no, it's just the output of the if config command is not showing it. Let's use this one. There you have it. It's assigned to ETR 0. And now I will even be more brutal and just demo what happens when the communication in the cluster fails between the nodes. So showing how fencing is acting. And therefore, I will just go back to node 1 and kill. I can't use a normal SIG hub here. I need to really hardly kill it, otherwise it would automatically restart. I kill the corosync process, which is responsible for cluster communication. You could also imagine a power failure and one node is down, or the network link between the node is broken or something. This is kind of to simulate this kind of failure. And it should sooner, this one is running on node 2, so yeah, you see node 1 is down, and in this is a virtual machine manager. You see I configured the Stonitz device to restart the nodes on failure. So this one was just stopped and started again, and is, well, should be up in a bit again and operate normally. Might take some time, but this is, you see, I need to disconnect once, and then you see it's already started again, so it should show up here as green, and all resources are running again on that server. So that's basically the demo part. And where did I have? Yeah, I'm mostly done with my presentation. So if there are any questions, just ask.
So, questions?
Would be more simple if we, in this scenario, to use Keep Alive, which is a solution for VRRP. Would it be more simple than Pacemaker?
I don't know that solution. What exactly does it do?
It uses the protocol VRRP at ARP level, in enlace level, and when one node's down, the other comes up, and you can configure and use scripts to shut down. I found myself wondering, because in this scenario we want to be able to use delta sync rep in a master-slave scenario.
Yeah, this one, sure, this one doesn't support delta sync rep. It's based on normal sync replication. But the thing is, this is just a start of a high availability server. You can easily extend it, be more, offer more service, like add load balancing to it, or add some more nodes that are read-only replicas and do load balancing, and all this is supported already in Pacemaker. So I think one reason for using Pacemaker is because it's offers more possibilities for enhancing the setup.
Okay, thank you.
You defined IP before slapd, I think,
Yeah.
while slapd is always active on both nodes, so slapd is always on, so might it be better to define slapd before IP?
In this setup, it's just a matter when, for example, one node was down. And it might make sense to define slapd before IP, so that you won't, you might be a smarter configuration, yes, right.
So, given this is HA configuration, and for example, normal SLA in LDAP world would be kind of 10 milliseconds of downtime. How can you fix that with a cluster? I mean, because I can see that the timeouts are 10 seconds.
You can use shorter timeouts, but you can't do 10 milliseconds or something. Then you would have too much load for monitoring. But sorry, oh, no. This one is for obviously for longer timeouts.
Right. I mean, I was asking for what would be the scenario, because from what I've seen, SLAs are usually much lower than.
Usually, you would put this one. This is the master server. Usually, you would have like multiple slaves before it, And the failover for that, there's, for example, the clients can fail over themselves if you give them multiple IP addresses of the read-only servers, or you have load balancer in front of the read-only replicas, or Linux virtual server, where the failover happens much faster. But for the master server, I can't offer currently faster failover times. But I think for write operations, that is okay. If you need faster failover for read operations, yeah, you have to implement something more.
Okay, thanks.
Any more questions? We've got time for one more, I think. Oh, up front.
So you were also talking about the load balancing features of Pacemaker. So I could just configure how does Pacemaker then measure the load? Does it measure the load and then intelligently switch to another one?
It's not Pacemaker. You can integrate Pacemaker with the Linux virtual server project. I don't know if you heard it, but there's good support in Pacemaker for integrating that, and so you can make the load balancer managed by Pacemaker. So if the load balancing fails, you can start it on different nodes, or Pacemaker itself does not do that. It's just for managing the Linux virtual server project code.
So, thank you, Ralf.
Yeah, welcome. Thanks. Yeah. Yeah, I kind of read that already, yeah.
Thank you, Ralf.
Thanks.